network problem today, but anyways, we'll try. Um, okay, so this is in full screen mode or not yet? Okay, so today we'll be again talking about waveguides and we'll quickly recap what we had discussed in the last class. And then what we will finally go into is mirror waveguides and dielectrics. So if you have layers of dielectrics, how that can also serve as a waveguide and what could be the typical cutoffs or how can one use this variation in dielectrics between different media and use this difference to make waveguides and characterize them in terms of their cutoffs, cutoff frequencies, and so on. So we'll try to work out the basic relations, and the questions typically in this sections generally come quite these are normally direct questions which make use of these concepts. So if you have any doubt while we discuss, you can ask. Okay? So uh, briefly, what we spoke about in the last class was about transmission lines and waveguides, and we saw that for a transmission line, you have two conductors, and there it supports TEM modes. But in normal metal hollow waveguides, it consists of one conductor and there it does not support TEM mode. Rather, we just have TE and TM modes. And how do we do that? Is that we started with the Maxwell's relations. And from there, we saw that at the inner wall, these were the two conditions that were supposed to be satisfied, right? And from there, these were the two conditions. And in order to satisfy these conditions, based on this, what we did is we wrote the electric and magnetic fields in terms of the different XYZ components and used the Maxwell's equations to get to this relations, which finally led to this, which said that now EX, EY, BX, and BY were dependent on the derivatives of EZ and BZ. So if one sets EZ and BZ to 0, that means, you know, all of these components will go to 0. So this was the reason why TEM modes did not hold for normal hollow metal waveguides. So here Z was the direction of propagation of our waves. Okay. And so basically that means we do have some component of electric and magnetic field in the direction of propagation of our waves. Right. And from this other two Maxwell's relations, we could get to this two relations, two differential equations, which were used to find an expression for the Ez and the Bz components. Okay. So there we saw that now if you have a TE wave, that is a transverse electric wave, that means Ez is 0. So there we used the separation of variables to find an expression for Bz, right? And this was the typical expression that one could get. And here M and N denotes the kind of mode that we are talking about. Okay. And from here we saw that these are the different kx and ky components of the wave vector, and from here you can get to an expression of a cutoff frequency. So below this cutoff frequency nothing propagates in a waveguide. Okay, so it acts as a high pass filter, right? And here for a mode we saw that the smallest or the lowest cutoff frequency correspond to this value where you put one, like the you can say, so m corresponds to the dimension which is the larger one, okay, among the two dimensions that are involved in this rectangular wave, right? And accordingly if you put m to be 1 and n to be 0, that corresponds to the lowest cutoff frequency that one can have in a waveguide, the TE mode. Okay, and below this nothing propagates. And similarly, so here there was interestingly one important point that so you can write an expression for the wave number. From there, you can find the expression for the wave velocity. And this is telling you that now the wave velocity is larger than the speed of light, right? Its wave velocity is greater than the speed of light. So if you try to write the, uh, you know, using this wave velocity, if you try to write the expression for the wavelength, you'll see that the guide wavelength is greater than what you have in the free space, right? But this does not violate anything because the energy is carried at the group velocity, and if you find the group velocity, it is still less than c. So everything is consistent. And so this is just another way of looking at it in terms of, we saw that if you look at it in terms of total internal reflection, we would get a similar expression for the group velocity or the frequency, right? So this was the take home message from here, that this is how the cutoff frequency is defined for a particular mode. So one can do a similar thing for TM modes, and there again, here EZ will not be zero, but BZ will be zero because it's a transverse magnetic mode. And the difference between TM modes was that here, because this comes from the boundary conditions, so here we set the boundary condition as Z, X going to 0 at X equal to A and X equal to 0. And in case of TE modes, if you remember, it was derivative of X, right? If you define the, uh, you know, longitudinal components like this, then there, in case of TE modes, it was the derivative of X, which went to 0 at X equal to 0 and X equal to A. Here for TM modes, we just put X going to 0. Okay. And from there, we get this expression for the electric field component. Okay. In the direction of propagation of our waves. And from here, you can find again the expression for the cutoff frequency. And you see that this is the same expression as what we have for a TE mode. Okay. Interestingly, because it's a sinusoidal function, that means here n and m starts from 1. So the smallest or the lowest TM mode will correspond to m and n equal to 1 and not 0. Okay. So this was about the TE and the TM modes. So even in the coming discussions that we'll have, so this concepts will always be useful as to what are the typical expressions of TE and TM modes. And there can be direct questions which, give you this form and ask you what is the mode that corresponds to. So there you have to compare this m and n with the expression that is given in the question to find the expression. Okay. So this is the interesting point to remember, that the phase velocity of waves propagating in a hollow metal waveguide is actually greater than the velocity of light in free space. Okay. And this comes from this relation that we had discussed in the last class. Okay. So now what we will be discussing about is planar mirror waveguides. So basically what it means is that you have these two mirrors, and we call it mirrors because the waves will get reflected when they reach these surfaces. Okay. There'll be multiple reflections of the waves. So here it says that you have these two parallel mirrors, and they're at a distance d from each other, and then you have a wave propagating through them. Okay. So here you can understand that when the wave propagates, they can have different kind of wave vector directions, right? So if you consider that the initial direction, so if this is the axis of your, so, the direction of propagation of the wave, if this is taken as z, then the angle that the wave vector makes with this direction of propagation can be taken as theta. Okay. Now, when the wave propagates, you can see that it will have multiple reflections. So if it starts from here, it will have a reflection here. Then again, it will have a reflection here. And for proper transmission, we do not want the waves to, attenuate or get the information should not get lost, right? So we do want minimum refraction. So we don't want any light to get out of this waveguide. We want the light to be confined and, transmit through the waveguide. So there, what's important to assure for proper transmission is this self-consistency condition, which says that the wave reflects. So when the wave reflects twice, so it starts from here, it reflects once here, and then it reflects again here. But once it reaches here, the self-consistency condition says that the wave here and the wave here is the same. So it reproduces itself at these two planes. Again, it has two reflections. Again, the wave here is same as what you had here and what you had here. So this self-consistency condition assures that your wave is actually, transmitting properly. Otherwise, though, so if this condition does not hold, then those kind of modes or those kind of waves cannot propagate through the waveguide, right? So now if you want to write this in mathematically, what do you say? So you say that as the waves propagate, they acquire some phase, right? So if we say that the wave here and the wave here is the same, that means the phase acquired must be a integral multiple of 2 pi. Okay, so that is what is being written here. So if you say that the wavelength is lambda and this is d, that means the phase difference that is acquired when the wave, after the wave has these two reflections. So you can say that 2 pi by lambda 2d sine theta should be equal to 2 pi m. Okay, and this, you can see, sets a limit or sets a condition on what are the typical theta values that are possible, right? And this is given as theta m. So theta m corresponds to, so for m equal to 1, 2, and all the integral numbers correspond to all those, uh, angles at which, if your wave starts with this particular wavelength, then they'll be able to propagate, right? So now, given this condition, if we consider that, you have some wave, so you will have a kx component, a kz component, which is along the propagation direction, and you will have a ky component. Okay, so when you say ky, that means it's perpendicular to the direction of propagation, right? So if you take the theta here, theta is the angle of the propagation vector with the k vector with the propagation vector, right? With the propagation direction. So k cos theta would give you the net wave number in the wave vector in the direction of propagation, and k sine theta will give you in the perpendicular direction. So if you say that the y component of the propagation constant is given as n k naught sine theta. So here, why is this n coming in? So the n is coming in because of the refractive index of your medium. So in free space, if your medium, if the wave vector is k, then in some particular medium with some refractive index n, your net k value will be n into k, right? And now you take the component in the y direction, so it's n k naught sine theta. Okay. Now here, what it says is that if you now apply this condition that you have found from the self-consistency case, that means that would give you a typical value of ky, which which will be possible, like which will satisfy the self-consistency condition, right? So this k values are the possible values of ky. And now you know that, if you consider the net k value, k is equal to ky square plus kz square. So there you can see that the propagation constant can be written as k square minus m square pi square by d square. Basically, it's just the modulus of, so k is the net modulus of your wave number, and this is in the transverse direction, and this is in the direction of the propagation vector. Okay, so this is the expression for the propagation constant. Now, this is already telling you that all waves cannot transmit, right? Now, here it's interesting that based on, so now if you want to pictorially understand what it means, it says that, so if you have different values of m, that corresponds to different kinds, different modes of your waves, right? And as you can see, because you have to satisfy this self-consistency condition, that means, so if you just look at it pictorially, you can see that the smallest, the wavelength that, sorry, not smallest, the largest wavelength, right? So the largest wavelength that is possible is the case where the wavelength is twice the distance between the two wave mirrors, right? So here, if this is d and this is half of your wavelength, so that means the largest wavelength possible for transmission would be 2 into d, right? So this is pictorially how one can understand. We will now in the next slide discuss how we can get to that mathematically as well. But from here, what we got to see is that there are some typical values of ky and, wave vectors, which can be propagated through the waveguides. And that depends on the distance that you have between these two mirrors. and the wavelength. Okay. So now here, as you saw that, sine theta m had this relation. So sine theta m can never be greater than 1. So that means that sets a limit to the maximum value of m that is possible. And what is m? M is denoting the number of modes. So this is telling us that there is a limit to what your m value can be. So there is a limit to what kind of modes you can have in a particular waveguide. Okay. And so if you consider this case, then you can set a maximum value of m, and that is given by 2d by lambda, right? So from here again, you can see that if your lambda is larger than 2d, then those kind of modes cannot be propagated through your waveguide, right? So this is the condition that you can see here. So if your 2d by lambda is less than equal to 1, which corresponds to the fact that your lambda by 2 is greater than d, there m is sent to be 0, which indicates that the self-consistency condition cannot be met. So in this case, if this is the condition, then this kind of wavelength cannot propagate. Okay. So there is a cutoff wavelength, and that is given as 2 into d. So this is the longest wavelength that can be guided by the waveguide that you have. Okay. And once you know the wavelength, you can also find the corresponding frequency, right? So this is the cutoff frequency given the speed of your transmission and the dimension of your waveguide, basically the distance between the two mirrors. So here one thing is interesting is that this is C when you are talking about free space. Now, if you have a different media, there you have to consider the velocity in that media. Okay. So there the refractive index will come in. And this is in, Hertz units. So if you want to write it in terms of angular frequency, you have to multiply by 2 pi. So these are, and interestingly, this is the same as what you had initially got for the TE mode case, right? If you go back and see what is the expression for the TE smallest mode, and you will have the similar expression. So now if this is your angular frequency, you can put it in the expression for your propagation constant. So this gives you the dispersion relation, which relates the wave vector or the propagation constant with the frequencies. Okay. And omega c is your cutoff frequency. So what we were discussing till now was about two mirrors, and then there are multiple reflections. Now what we are trying to talk about is planar dielectric waveguide. So what do you mean by dielectric waveguide? Is that here you have different dielectrics with different dielectric constants, but they are arranged in such a way that when you have a wave, the wave of some particular mode and some particular wavelength, they would transmit through this medium. There would be, so you have to ensure that the loss or refraction or losses from this ends would be less, and you can say that the wave gets propagated in a particular direction. So that means there has to be a selectivity in this. So when you have some wave, the refractive indices has to be such, or the dielectrics should be such, that your wave remains confined and propagates in a particular direction. So one of the easy ways of assuring this is to arrange it in such a way that you have total internal reflection. So if you remember, in total internal reflection, we know that you have a denser media, and if you have rarer medias surrounding it, as the wave passes from denser to rarer media, the wave moves away from the normal. So beyond a certain incident uh, angle, the entire wave or entire gets reflected, right? So here again, so you can have the same concept. So you can have some dielectric with some dielectric constant N1, and then you put two dielectrics on the two sides whose dielectric constants are smaller than the one that you have in the middle. So the one in the middle is called the core, okay, while the one at the sides is called the cladding of the waveguide. So this is a planar dielectric waveguide where you have multiple media stacked together with a denser media in between and two rarer media on the sides. So now we know that if you have some wave and if the wave is incident in such a way that the incident angle is greater than the critical angle, then the entire wave will be reflected back. Right? And that is what we want to assure. Okay. So now here we have to set a relation between, so if this is your incident angle for this surface or the interface between the two media, and this is your theta. So theta is the angle that your wave vector makes with your direction of propagation. So you can see this makes a right angle triangle. So that means theta and the incident angle are complementary to each other, right? So theta plus theta prime or theta bar is equal to 90. So that means you can say that the condition that you have. So if you remember, we had an expression of critical angle, right? It's sine inverse of n2 by n1. So here the critical angle in terms of, so if you have to define taking into account this angle, the angle that it makes with the direction of propagation, then we have to talk about the complement of that, which is cos inverse n2 by n1. Okay, so that's why the cos term comes. Basically, what we are trying to do is we are trying to look at only those waves where the wave is incident in such a way that when it gets to this interfaces, they get reflected at an angle greater than the critical angle. Okay. So now if you have some wave, okay, with a particular wavelength, and here you can say the refractive index is n1. So if the free space wavelength is lambda naught, then the wavelength in this media will be lambda naught by n1, and then it is bouncing back at an angle smaller than the complementary critical angle. So that means you are ensuring total internal reflection. Okay, the wave is traveling with phase velocity given as C1 equal to C naught by N1 because of this refractive dielectric media. Okay. And the wave number again becomes N1 into K naught. And you consider that you just have wave vector components where Ky again is defined as K1 K naught sine theta and Kz is N1 K naught cos theta. Okay. So now we'll again the same, will apply the same self consistency condition. So that has to be always satisfied for the wave to propagate along the waveguide, right? So that means this is telling us that AC and AB, the phase difference between this. So if you consider geometrically, we know that the phase difference is 2D sine theta. Okay. So as the wave propagates, it acquires a phase shift. And this phase shift is because of the propagation. So that is given as 2 pi by lambda into 2D sine theta. Okay. Now another phase change comes or additional phase comes because of the reflection. So for a mirror, in the last case that we had, this, so if you use the Stokes treatment, one can say that reflections from a mirror causes a phase change of pi. Okay. But now because if you have a dielectric and you have waves, incident at different angles, so here it would not be this trivial. So you have to consider some phase. So for now, we consider that the phase shift because of reflections is taken as phi r. So because you have two such reflections, so you consider the phase acquired to be 2 phi r. Okay. So now this net phase, that is phase change that has happened, should be equal to 2 pi m. This is after two reflections. Okay. So the only difference from the last case here is that now you have this phase, the phase change coming because of reflections at the interfaces, and this is not pi like the case for the mirror. So here, this phase change, as you will see in the coming slide, depends on what is the refractive index of your core, what is the refractive index of your cladding, and what kind of, what is the angle of incidence, what is the polarization of your light. So this phase change depends on all these factors because now you are talking about multiple reflections in stacked dielectric media. Okay. So let us first, recall our concepts of, reflection and refraction from, when you have an interface. And we remember, let us recall that from the Fresnel coefficients, one can get an idea about, what kind of phase can come in when you have this kind of reflections. Okay. So here if you remember, if you have some media of dielectric constant N1 and some another media of dielectric constant N2, and there is an incident wave, a part of it gets reflected and part of it gets refracted. So this is a normal case. Now here we had initially solved this, and we saw that the typical Fresnel coefficients look like this, right? Based on how the lights are incident and refracted. This is for a T polarized light, and this is for TM polarized light. So these are the Fresnel equations. So now this is telling you that based on your theta, your reflection coefficients can become imaginary. Why? Because so if you look at how you know the so suppose if you talk about this refracted angle, so here it depends on the two refractive indices of the media, N1 and N2, by this Snell's law, right? So here, if depending on what is this ratio, or how N1 and N2 vary from each other, you can have a condition where theta 2 becomes imaginary, right? So in those cases, what would happen? Your reflection coefficients will become complex quantities. And because it can become complex, that means it can have a modulus, and it can also have some phase. It can result in some phase shifts. So that means now, because of this case, so because of the difference between the two refractive index and the angle of your incidence, based on that, you can have phase shifts. So let us take particular cases and see. So if you consider T polarized light, so that means you're talking about this relation. Okay. So here in this case, if you consider the case where N1 is less than N2, so that means you will have external reflection. So what this is telling you is that now if you put theta 1 to be 0, that is normal incidence, you would get this expression. This is the magnitude of your deflection coefficient, right? And as you change your angle, so as your angle changes and gradually goes to 90, your magnitude increases to unity. And if you look at the sign, you would see that you would have a minus sign always, which is telling you that you have a pi phase change. So this is the case for the condition where N1 is less than N2. Okay. So in that case, you will always have a pi phase coming in, and this is how the magnitude of your reflection coefficient will change based on what is your incident angle. Okay. But what we are more concerned about is internal reflection, because that is what matters for our transmission through waveguides, where N1 is greater than N2. Okay. So again, here, if you put theta 1 to be 0, you would get an expression like this. Okay. And gradually, as you increase theta, your value increases. So you're again working with this expression. Okay. So here again, what happens? It increases and it reaches 1 at a particular value when your incident angle matches the critical angle, right? Basically, at that point, you would get R to be 1. Okay, so this is the critical point where your reflection coefficient becomes 1. And beyond this, it remains 1. So that means beyond, this is the reason why if the light is incident at an angle greater than the critical angle, all of the light gets reflected, right? And if you look at now the phase, which comes from the fact, so now you can write it, just rearranging these terms, and you can write it like this. So here you can see that it can result in a net phase. Okay. And this net phase satisfies this condition. Okay. So that means if you look at how the phase, so this phase phi x looks like, you would see that it would be 0 till a particular incident angle, and then it would gradually rise to pi. Okay. So this is telling you that now your phase change depends on your incident angle by this relation. So this is the relation. So you can do similar things for TM polarized light as well. Okay. The equations then will be based on this relation. So now that we know that this is how your phase shift happens, and this is how it is related to your incident angle, we can now try to put it in our expression of the self-consistency condition, right? So this was the self-consistency condition, if you can remember. So here, what we will next do is we will try to put the expression of phi. Okay. So use this relation basically. Okay. So if you use that, you end up getting this expression. So here what you have done is you have converted from cos terms to sine terms, okay, by using these relations. So now this is the self-consistency condition for TE modes in a planar dielectric waveguide, okay. And what is this telling you is that now if you plot it, this is a transcendental equation. So you have to plot it like you have to plot the left hand side, you have to plot the right hand side and see where they intersect. Okay. And as you can see, it would intersect at some discrete points till a certain point. So what sets this limit? So what sets this limit is that your theta should be less than theta c. So here you're talking about the angle that the wave vector makes with the direction of propagation, right? So total internal reflection will happen when theta is less than theta c. So that sets a limit to the maximum value of sine theta that you can have. Okay, so that sets this limit. And then you count the number of times your these two relations, have a common intersection. So these are the specific values of modes that your waveguide can, hold, or these are the modes that can transmit, basically. So if you look closely here, each of these points are lambda by 2d, right? And lambda by 2d correspond to in the modes that we had initially talked about for planar mirror waveguides, right? So in the when we had initially seen here, we had this expressions, right? So lambda by 2d, sine theta m was m into lambda by 2d. So this was the case for planar mirror waveguides. Now it has changed to this intersection points. Okay. And you can see that if this is the limit, so suppose here for this kind of plot, here sine theta c is given as 8. So it strikes at 8 lambda by 2d. And if you count, you would see that you would have 9 modes. So that means if you know what is the relation between your sine theta c value and your lambda by 2d, and if you find the ratio of the two, okay, and from there you can get an estimate of the number of modes that your waveguide can support. Okay, so this is the ratio that we are talking about, right? So if you find the ratio between sine theta c and lambda by 2d, that gives you the maximum number of modes that can propagate through your waveguide. Okay, so so here if it is a non-integral value, then we take it to increase it to the nearest integer. So if it is 1.1, you take it as 2. Okay, so basically it comes from here. So if it is 8, you can see there are 9 intersection points. Now there could be interesting or you can say useful relations that can be derived from this. Okay, so what you can say is that you can write the same expression as m equal to 2d by lambda naught into Na, where Na is defined by this relation. So here N1 and N2 are the refractive indices of your code and clad. Okay, and this is what is called the numerical aperture. So basically this is the sine theta value. So this is nothing but this just gives you the, so if you think about it physically, numerical aperture gives you a range of values of theta c till which light or your wave can be collected. Okay, so it sets a limit to, so if you talk about, even in optical fibers, if you talk about numerical apertures, or if you talk about objectives and the numerical aperture of objectives, in all those cases, the physical understanding is same. So it takes into account what is the angular range till which your light can be collected. Okay, so and that depends on this refractive indices. So this is one of the important, you can say, parameters of for defining a waveguide. Okay, numerical aperture, and this is how you can write the number of modes in terms of the numerical aperture, the dimension, and the wavelength. Okay, so here you can see that now if you know N1 and N2, if you get an idea about the numerical aperture of your dielectric waveguide, you know the dimension, okay? And suppose if you are working with some particular lambda, so you know that if this condition, so if lambda by 2d is greater, lambda by 2d is greater than sine theta c, what would that mean? So that would mean is your m would, this term would go to less than 1, right? So in those cases, only one mode is allowed, which is this starting mode, which corresponds to m equal to 0, right? So that means in those conditions, the waveguide is called a single mode waveguide. So if there are situations where you are asked to find, what is the condition for a single TE mode or single TM mode to transmit, then you have to consider this relation. So basically, you have to put what do I say? So you just take into account this condition that now your lambda by 2d is not much, but just greater than sine theta c. Okay. So this corresponds to the case where m is equal to 0. So now if you know this, you can also write it in terms of frequency. So basically you're just converting from wavelength to frequency, and this is how it's related. So here what you are using is nu equal to c by lambda, and in place of lambda, what you are putting is, if you put m equal to 1, then what would happen? You would have lambda by 2d equal to sine theta c. So lambda equal to 2d sine theta c. Sine theta c, if you write it as Na, so it would be nothing but lambda equal to 2d Na, right? And that is the relation that you have put. C by lambda, replace lambda by 2d into Na. So this is your mode cutoff frequency. Okay. So there could be questions like, so one of the assignment questions in the last year was something like this, where you have the wavelength specified, you know the D, and you know the refractive index of the surrounding media. Basically, you know the refractive index of the cladding. And it is said that determine the maximum allowable refractive index of the slab material or the core, or am I saying the, yeah. So in that case, and maximum allowable refractive of the slab material, which would allow single TE or single TM modes, right? So there, what you have to, now you know N2, you know lambda, you know D. So basically, you just don't know N1. So put M to be 1. So lambda then becomes 2D NA, and use this relation. Okay. So here, if you use this relation, you can see what is the, basically try to find N1. So this is how this kind of, there could be very direct questions based on this formula. So this was one of them. So whenever it says this allow single TE, that means you're talking about single mode waveguide. There could also be questions which just, talks about this particular thing. So we know that there's a cutoff. Okay. So the cutoff, this relation. So the cutoff wavelength, there could be direct questions based on this. So if your D is given, what would be your cutoff wavelength, and questions like that. It's important to note that the because of this relation, because the phase velocity is greater than the velocity of light, you can be asked to find the, what is the guide wavelength. So in case of guide wavelength, that means the wavelength inside the waveguide. And because the phase velocity is greater than velocity of light in free space, that means the wavelength inside the, so if you talk about a particular wavelength, particular wave of like monochromatic wave or monochromatic light, then the wavelength will also be greater than what you expect in free space. Okay. So that relation comes from this relation here. So now that you know how velocity goes, you can try to write an expression for the wavelength. So basically, again, you will have a similar expression. Basically, it will be lambda into lambda free space by root over 1 minus omega free space by omega omega cutoff by omega free space, right? So in terms of frequency, it will be something like that. In place of wavelength, then it will be lambda by lambda c, something like that. Okay. So basically, you have to use this relation that because your wave velocity is greater than speed of light, your effective wavelength in the waveguide will be greater than that expected in free space. Okay, so there could be questions along these lines. Yeah, that's it. Do you have any questions?
Ma'am, in previous sum,
Yes.
you said you have to substitute m equal to 1 and but we cannot able to find what is it.
Uh,
So,
I'm unable to understand what you're saying. Can you please repeat?
ma'am, previous question lambda equal to 1 by 1.55 micrometer and the thickness of the slab. You explain one problem now.
Oh, so this one. So here you have the wavelength
M
given. Yes, yes, tell me.
D, yes, ma'am. Here you said you have to substitute m equal to 1.
So
So how
basically,
we can solve?
so here what we are trying to do is, it is saying you just have one single TE or TM mode, right? So if you put M equal
Okay.
to 1, that means your lambda becomes 2D into NA, right? And that is what actually you have used here. When you write nu equal to C by lambda, right? So C is the speed of your wave and lambda is your wavelength. And in place of wavelength, you write it in terms of your numerical aperture of your waveguide into 2 into D. So now in this question, what it is saying you is your wavelength is given. Then, so this wavelength is the wavelength in free space, right? And
Right.
now the slab thickness is given, which is given as 1 micron. So that means D is given. The refractive index of the surrounding material is N2. So that means here you know N2. And you have to determine the maximum allowable refractive index. So you have to find N1. Yes. So basically, this information will go into finding C naught. This is your wavelength for free space. Basically, lambda naught, right? So what I was talking about is the effective lambda in the waveguide. Here, this is the free space wavelength. Hello.
Okay, ma'am. Okay. Okay, ma'am.
Yes. Any question? Anyone? Okay. So if not, uh, let's call it a day. Okay. Thank you.
Ma'am, hello.
Yes. Yes. Yes.
Uh, Here, how we can find cutoff frequency and propagation constant, wave impedance, ma'am?
Yes. Yes. The just repeat. Actually, your voice is breaking. I'm not. Wave impedance of.
Ma'am, propagation constant of given dielectric slab.
Okay. So see. So propagation constant is this, right? Propagation constant is this for any particular question. If you can find the cutoff frequency, then you can use this relation to find the propagation constant, right?
Okay,
So
okay,
that
ma'am.
is yes. But now when you talk about wave impedance, basically these are all along the same lines. So oh sorry. So here 1 second. I'll show you the relation maybe. So so see the wave velocity is reduced by this relation, right? So inside the waveguide. So as you can remember, see, when we normally define a wave impedance, we define it as root over mu naught by epsilon naught, right? Now you would have this additional term coming in because of your relation between the cutoff and your incident frequency. So if you have to write, so you know the wave impedance in free space, right? That is 377 ohm, right? Now, if you know the cutoff frequency in your for your waveguide, okay, and you know the incident uh, frequency of your incident signal, so that means then your impedance will be affected by this factor. So it will be 377 divided by this term that you see here. This is in terms of frequency. Now, if you have to do it in terms of wavelength, this ratio will get reversed, right? Is that
Okay, ma'am.
is that clear?
Clear, ma'am.
I'm losing your voice, but you can also write. I can checkbox. I'm unable to hear you properly.
Okay, ma'am. Clear.
Okay. Basically, just find the cutoff frequency and do the ratio of the two. 1 minus that whole square, 1 by this thing. 377 divided by that. Because your wave velocity is changing, so all the terms, your effective wavelength will change, your the impedance that the wave sees will change by the similar relation. Okay. Any more questions? Okay. So if not, thank you everyone. I'll stop sharing. Thank you.